Hello and welcome back to Data Analysis and Visualization. I'm Javita Christie, and in this video, we're going to talk about dimension reduction. First of all, why do you need to reduce dimensions? So many times when you're working with large data sets with many dimensions, things get too computationally expensive and confusing to keep track of because you have so many dimensions. Um, Most of the time, you're not just working with two-dimensional data, which is just x and y axis. There are many dimensions involved, and the more the number of dimensions, the more you need to uh, use resources computationally. So, for example, if you were applying a clustering algorithm, then that algorithm would take less amount of time and less processing power running on a two-dimensional data versus a data that is, say, 10-dimensional. However, many times we look at the data itself and we see variables that are strongly correlated and hence possibly redundant. For example, a person's height and weight. So many times when we look at data, we can actually reduce the dimensions, the number of dimensions that we have. For example, if we had a person's height and weight, do we really need both? Because most of the time, just having a person's height can, help you to predict the weight or weight based on the height. Or if you know a person's weight, you might be able to predict a person's height. So most of the time it's correlated. So having one means you do not need the other one. So you can reduce some of the dimensions just by looking at your data. Now, what if there was a way to reduce the dimensionality of our data while still retaining its information? So while reducing dimensions, we don't want to lose information. We want the information that we have to remain in your data still. So to reduce dimensions without losing information is something that we are aiming for. And to do that, we use a technique called PCA, which is known as Principal Component Analysis. And I'll be showing that to you in a minute. Now take a look at this data. What has been done here is all the dimensions of the data are plotted. And if you see the plots, then if you just compare this plot with this plot, you can see how similar they are, right? They look alike. So if you have data which looks like this, if you have two dimensions which look like this, then you can essentially, remove one of those because they are giving you the same kind of result. Now, what is PCA, which is Principal Component Analysis, and is used in performing dimension reduction? So PCA is an algorithm that compresses your data set's dimensions from a higher to lower dimensionality. So if you have 10 dimensions, you can reduce the dimensions and make it 7 by using principal component analysis. And it does all this based on the eigenvectors of the variance in your dataset. And I'm going to explain these eigenvectors to you in a little while. PCA is widely used in data compression, saving loads in processing time, as well as in visualizations of high-dimensional data in 2 or 3 dimensions. This is very helpful when you are doing cluster analysis. So PCA is mainly used for data compression because if you reduce the dimensions in your data set, you are indeed compressing your data set as well. But it can also be used in data visualization because if you have 10-dimensional data, you cannot really plot that onto anything because it's 10-dimensional and we can only perceive like 2 or 3 dimensions. So if you want to plot a 10-dimensional data in 2 or 3 dimensions, you can use PCA there as well. And PCA is helpful in cluster analysis also because if you reduce the number of dimensions in your data set, the cluster analysis will take less time and it will also consume less resources like processing. Now, more technically, PCA finds a new set of dimensions such that all the dimensions are orthogonal, which means they are linearly independent. What are linearly independent dimensions? That means one dimension does not depend on another one linearly. For example, height and weight. We know that height depends on weight, weight depends on height. So if height increases, weight increases, height decreases, weight decreases. So PCA finds a new set of dimensions in such a way that, either height is removed or weight is removed, because if you have one, you can always get the other. And PCA also finds these dimensions such that they are all ranked according to their variance of data along with them. This means the first principal component contains the most information about the data. So if you have 10 dimensions, PCA is going to convert that into maybe 7. And out of those 7, the first one is going to be the one that has maximum information about your data. It impacts your data the most. Now, how exactly does PCA work? So first of all, you will calculate the covariance matrix X of the data points. This is how you know how the variables are related to each other. So if you know mathematics, about matrix and all, you probably know what a covariance matrix is, and you've probably calculated dozens of these things. But if you don't know mathematics, if you're not mathematically sound when it comes to matrices, then I am going to give you an intuitive example that can help you to understand all these things. So either way, you don't need to worry if you don't understand the terms that I'm going to use here. So the second step after calculating the covariance matrix is to calculate the eigenvectors and their eigenvalues. Once you've done that, you will sort the eigenvectors according to the eigenvalues from largest to smallest. So in descending order. So 3 steps: covariance matrix, eigenvectors, eigenvalues, and then sort eigenvectors according to eigenvalues from largest to smallest in descending order. Fourth step is to select a set of eigenvectors k to represent our data in k dimensions. So depending on how much reduction you want to do, you will select the value of k. So if you want to reduce out of 10 dimensions, you want to reduce 3, then you can select k as 7. Transform our original n-dimensional data set into k dimensions. So that's the final step, transforming the original data set with n number of dimensions into k number of dimensions. Now, what are eigenvectors and eigenvalues? Here I'm going to explain it mathematically. Later I will explain it intuitively. So, eigenvectors or principal components of our covariance matrix represent the vector directions of the new feature space. New feature space is the space that we've calculated now after performing PCA. The eigenvectors represent eigenvalues represent the magnitude of these vectors. Now, vectors we know are always having a direction attached to them, but they also have a magnitude. So eigenvalues, they quantify that. As we are looking at our covariance matrix, the eigenvalues quantify the contributing variance of each vector to the overall variance in our dataset. So each dataset has its own variance, but how much does each vector contribute in towards that variance? That is given to us by eigenvalues. Now let's take a look at an intuitive example. This is not mathematical at all, but it's a real life example that can help you to understand all these things about, matrix and eigenvectors and eigenvalues, even if you do not have a mathematical background. So imagine you have a bunch of people. Every person has a group of friends they talk to with some frequency, and every person has a credibility rating, though the same person may have different credibility ratings from different people. So you have a couple of people, you have 100 people, Okay, every person in that group has his or her own group that they are talking to. So you might have a bunch of 100 people, but out of those people, and maybe I'm one of them, and I am not talking to all 100 people. I'm talking to maybe 5 or 7 of those people, because those are the people who are in my social circle. So I'm talking to these 5 or 7 people. So even though I'm talking to 5 or 7 people, I'm going to give a credibility rating to each of them differently, because out of those 5 or 7 people, there might be one or two that I'm really close to, or that I'm best friends with. So for such people, I'm going to give a higher credibility rating, which means if they tell me something, then I'm more likely to believe it because I trust those people more. So I'm giving them a higher credibility rating. But for the rest of the people, I'm going to give them a lower credibility rating because um, I trust them less. So this is how it's working. Now it's possible that, I out of 10, I am giving a rating of 9 to somebody because I am really close to that person. And so I trust that person more. But somebody else might give a credibility rating of 7 to the same person because they don't know them as I know them. So this is the scenario. Now you distribute an amount X of gossip to each person and let them talk to each other. Okay, so X is the amount of gossip that you are giving to each person, and it's different for each person. So let's say that to person A, I am feeding 10% of gossip. To person B, I'm feeding 20% of gossip, and so on. Okay, and then you allow all the 100 people to talk to each other. The largest eigenvalue gives you an idea of the fastest rate at which gossip can grow in this social circle. Okay, so it's a social circle, and eigenvalue would give you would give you an idea of how the gossip is growing. So if you find the largest eigenvalue, it will tell you the fastest rate at which this gossip is growing in this social circle. The corresponding eigenvector to this eigenvalue will give you an idea of how much gossip each person should start with in order to obtain this maximal growth rate. Okay. So in particular, if you want a story to spread rapidly, the largest components of the principal eigenvector identify who you should tell the story to. Okay. So if you have the eigenvector that corresponds to the eigenvalue will tell you how much gossip each person should start with in order to obtain the maximal growth rate. So remember you decided 10% to this one, 10, 20% to this one. So eigenvector would tell you how much percentage to tell to each person so that the gossip is spreading really fast, the maximal growth rate. So if you want your rumor, your story to spread faster or the largest, then what should be the largest component of the principal eigenvector? And you can identify that. So you'll probably know now which person to tell it to so that it's going to spread the fastest. Now, let's take a look at this example here, which is what happens once you perform PCA. So this is the original data set. Okay, it doesn't matter what it represents right now. But essentially, it's a data set that has many dimensions, but it has now been visualized as within a two-dimensional space. Okay, now once you perform PCA, the same data set is going to look like this, because now instead of 10 dimensions, it is having maybe 7 dimensions. So it looks different when you plot it on a 2D space. Now, some of the points to remember when you're dealing with PCA is always normalize your data set before performing PCA, because PCA is very gets very much affected by outliers. So you have to normalize your data set. Principal components are always linearly independent because that's the idea. If something is linearly dependent, you try to remove one of those dimensions. Every principal component will be orthogonal or perpendicular to every other principal component. So this is something opposite of being linearly dependent. Linearly dependent would mean it goes up in a straight line, but orthogonal or perpendicular would be a 90-degree dependency. Using PCA, we can use k dimensions to represent some value, always less than 100%. Your goal would be to get it as close to 100 as possible with as small k as possible. So we want to reduce the dimensions, but not at the cost of losing a lot of information about our data set. So because you're performing compression, you will lose some information, but you don't want that to be, let's say a 70% loss. You want the information to still be 100% correct or as close to 100% correct as possible with the least number of dimensions. And numerically, to compute PCA, you use a technique called SVD, which is singular value decomposition. The goal of PCA is to create a new data that represents the original with some loss due to compression or reduced dimensionality. So there is a loss of information, but not a lot of loss, just some loss. Let's take a look at some of the disadvantages of PCA. So PCA works only if the observed variables or data is linearly correlated. If there is no correlation within our dataset, then PCA will fail to find the adequate components to represent our data with less dimensions. Okay, the PCA relies heavily on linear correlation. If there is no linear correlation among your dimensions, then PCA has nothing to remove. Okay, so like I explained earlier, height and weight are linearly correlated. One increases, other increases, one decreases, the other one decreases. And that's why you can choose to remove one of them. You can remove either height or weight, because if you have, say, height and if you remove weight, you can always get predict with some with quite a lot of certainty the weight given the height. So that's why you can afford to remove the weight. Okay, so there is a linear correlation. But if there is no such linear correlation among your data set, among your variables in the data set, then PCA will fail to reduce dimensionality. PCA by nature is lossy, and thus information will be lost when we reduce dimensionality. Okay, and it is also sensitive to scaling, which is why you have to normalize your data set before starting. Visualizations are hard to interpret real meaning because they do not relate to the original data features. So although PCA can be used to visualize a 10-dimensional data set into a 2-dimensional space or a 3-dimensional space, such visualizations will be really hard to interpret because, imagine seeing something 10-dimensional in a 2D or a 3D space. You won't be able to make out what it means. Okay. So this is where I'm going to end this video, but I'll be back with the next one. So I'll see you there, and thank you for watching.